All right, this is AP BC Calculus. We are doing Unit 9, Section 7, which is a BC only topic. We're defining polar coordinates and differentiating polar forms. So let's do a quick review about polar. So a review from pre-calc about polar coordinates. So a point in polar is written as r comma theta, right? So r is the directed distance. So r is the directed distance, and so they just wrote regular distance here, but technically it does have a direction. So r is the directed distance from the pole or the origin, right? So this is called the pole in polar, but it's the same spot as the origin, to this spot, right? To P, whatever point P is. And theta is the angle from the positive x-axis, which we call the polar axis. So the positive x-axis in polar is called the polar axis. So theta is the angle measured counterclockwise from that positive polar axis, which is why we also see that when we do stuff like what we did in pre-calc with the unit circle, right? We always rotate counterclockwise as positive. So we'll also talk about how to convert between polar points and Cartesian or rectangular coordinates in the next slide. But before we do that, let's plot a couple points in polar. So I was lazy and I just typed pi instead of the pi symbol. So let's plot, so we'll do this one in blue. Okay, let's plot 2 comma pi. So the first thing I'm going to do is I'm going to look in the pi direction, right? This is pi, right? There's pi right there. And then from the pole, I'm going to go out 1, 2, and there's my point. This is the point 2 comma pi, okay? In a different color, let's pick red. I'm going to do 3 comma pi over 6. Well, I'm going to start by going facing the pi over 6 direction and then the start of the pole and walk out 1, 2, 3. And that point right there is 3 comma pi over 6. And then the last one's a little bit tricky, so we'll do this one in green. I'm going to start, it's a negative 4 comma 5 pi over 3. So I'm going to start where 5 pi over 3 is, which is right here. But then instead of walking this direction, right, I'm not going to walk towards 5 pi over 3. I'm going to walk backwards, right, 4 units, which is going to be to 2 pi over 3. So 1, 2, 3, 4. Okay, this is the point negative 4 comma 5 pi over 3. It is worth noting that it is the same point as a regular 4 comma 2 pi over 3. So same spot. Again, I faced the direction 5 pi over 3, and then I walked backwards because r was negative, which is why I said that this should actually say directed distance, and there's a typo there. It only says distance. All right, so let's talk about converting between polar and rectangular coordinates. So polar is r comma theta, right? Rectangular coordinates is x comma y. So you actually know enough to do this without me. You can look at this triangle, and there are 4 formulae that you can get involving x, y, r, and theta, right? So let's go ahead and walk through this. First thing I want is an equation that relates x to y to r, right? Well, that's definitely x squared plus y squared equals r squared. That's just Pythagorean theorem. So thanks, Pythagoras. Right? Next, I want one that relates x and r and theta. Well, that's just cosine, right? So cosine of theta should be x over r. The way we're usually going to write this is x equals r cosine of theta. So that's going to be kind of useful, right? Then I want one that relates y and r and theta. Well, that's so. So the sine of theta is y on top of r, meaning I can write this as y equals r sine theta. And the last one is one that relates x and y and theta, right? Well, x and y and theta, that's going to be tangent, right? So the tangent of theta is y over x, and that's the other equation. So the equations that you could need to convert between rectangular and polar or vice versa are all things that you learned in sort of basic geometry. I don't have any of these memorized. I understand that this is how they work. I know this is basic algebra and basic geometry, and so then I just kind of figure it out as I need to. But you obviously need to figure out what works for you in terms of what you have memorized. Let's keep moving. All right, so in calculus with polar curves, we're going to need to do the following skills. We're going to need to be able to differentiate polar curves, find tangent lines, determine the area enclosed by polar curves, and find the arc length formed by polar curves. So in this video, right, so this will be 9, 7, right? This will be 9, 8, and a little bit of 9, 9, and I believe this is 9, 9. Yeah, so that's the plan. All right, so we've already seen in parametric that the slope of the tangent line is always dy dx, and in parametric we had to use dy dt over dx dt. Well, here it's the same thing. We're going to use dy d theta over dx d theta, right? Because the logic behind this is that this is dy d theta times a d theta over dx. These cancel, and I get a dy dx, right? What makes this a little bit harder is that since y is r times cosine theta, and r is often not a constant, because if r were a constant, we wouldn't need calculus. You'd just have a circle. I'm going to end up having to use the product rule. So to find dy d theta, I'm generally going to have to use the product rule. To find dx d theta, I'm going to have to use the product rule. So there are two ways to do this. You can either memorize this, which is fine, right? So remember that that y was r sine of theta, right? So this is u dv plus v du, fine. And remember that x was r cosine theta, so this was u dv plus v du, and that's fine, right? So if you want the tangent line, it'll be dy d theta, which is this thing on top of dx d theta, and you can straight up memorize that. That's fine. Or you can say, hey, I'm not going to memorize it, and I'm going to have to do the product rule every time. I really don't care. I don't have it memorized. But I probably would if I were doing a bunch of polar problems in a row. It's been a while since I had to just sit and do a ton of polar problems. So that's up to you whether you choose to memorize it. I think that choosing to memorize it is risky because you can easily forget a negative or forget what thing is prime. So, it's up to you. I just do the product rule. So we're going to find the equation of the line tangent. So notice I want the equation of the line tangent. That means I need two things. Number one, I need a point. Well, my point is going to be x comma y, not r comma theta, right? Because I want the equation of the tangent line in terms of x and y. That's how we would get this line, right? So my x is going to be r cosine of theta. My y is going to be r sine of theta, right? In this case, my r is a 2 theta, right? So 2 theta cosine theta and 2 theta sine of theta. So to find my point, I need x of pi, right? Well, that's going to be 2 pi cosine of pi. I'm pretty sure that's a negative 2 pi, right? Because cosine of pi is a negative 1. And my y of pi is going to be a 2 pi times a 0, because that's what sine of pi would be, so I get 0. So right away, my point is a negative 2 pi comma 0. That's the point I need. Now, the second thing I'm going to need is the slope, right? And that's going to be the one that's a little bit more difficult, right? So I'm going to need the slope, which I know is going to be dy dx. So I'm going to have to find dy d theta over dx d theta. So I'm going to get that my dy dx, right? So let's go ahead and start with this guy. It's my u and my v, right? Dy d theta is going to be u dv plus v du. And dx d theta is going to be u dv plus v du, right? So I don't really have to clean that up. I mean, you can if you want. There's not really a huge incentive because I'm about to just plug in pi anyway. If you want to clean it up, you certainly can. It doesn't matter at all to me if you do. So when I clean this up, I want my dy dx at the moment when theta is pi. Well, that's going to be 2 pi times a negative 1 plus a 0, because sine of pi is 0, over a 0 plus a 2 times a negative 1. I think I get a negative 2 pi over negative 2, so I think I just get a pi. So once I have my point and my slope, my answer is y minus the y value equals mx minus the x value. And that's my answer. You don't need to write the 0 if you don't want, right? You could just write this as y equals pi times x plus pi over 2. You could distribute. I just think that's a weird choice. There's no reason to do extra math if you don't have to. All right, let's try the same thing for P1, right? Again, equation of a line tangent, so you need both a point and a slope. Your x of theta is r cosine of theta, right? Which means that x of pi over 2 is going to be 5 pi over 2 times 0, or just 0, right? Y of theta is going to be r sine theta, which means y of pi over 2 should be a 5 pi over 2 times a 1, or just a 5 pi over 2. So I have the point, right? So that's the first step in the problem, right? My point is 0 comma 5 pi over 2. Great. Then I need a slope, right? So my slope is going to be dy dx, but we know that that's dy d theta, which is a product rule over dx d theta. And again, I don't have the formula memorized. If you're the person who does, great. So for dy d theta, right, there's my u and my v, and here's my u and my v. So I'm going to get u dv plus v du on top of u dv plus v du, right? And I want dy dx evaluated at pi over 2. It's not an accident that I picked values that would knock out all of the cosines, just like in the last one I knocked out the sine. So this is going to be a 0 plus a 1 times 5. And here I'm going to get a 5 pi over 2 times a negative 1 plus a 0. Right? So it seems to me that I end up with a 5 on top of a negative 5 pi over 2, which is a 5 times a 2 over negative 5 pi. So I think I get negative 2 over pi as my slope. Oh, my bad. So my answer should be y minus the y value equals my m, x minus the x value. And again, you don't have to write it as x minus 0. You could just, if you want, you could even just make this a negative 2 pi over x plus the 5 pi over 2, and that's fine. All right, moving on. Okay, so we're going to find only the slope of this tangent line because that's going to be tedious enough without extra work here, because good times. So this time my r is a more complicated function of theta. So x of theta, right, is going to be r, which is cosine of 2 theta, times cosine of theta, right? And y of theta is going to be r, which is cosine of 2 theta, times sine of theta. So in both cases, I'm going to have to do a product rule. And if this is non-calculated, then I'm just gutting this out, and it is what it is. So my dy dx is the derivative of theta with y with respect to theta over the derivative of x with respect to theta, and both of those are going to be product rules. So dy d theta is going to be u dv plus v du is going to be a negative 2 sine of 2 theta, right? So because of the chain rule, right? On the bottom, I'm going to get u dv plus v, and then du is that negative 2 sine of 2 theta again. All right, so then my job is to plug in pi over 2. Again, not super fun, but we'll make it work. All right, so I'm going to get that this is cosine of 2 pi over 3, right? Cosine of pi over 3. And a sine of pi over 3 times a negative 2 sine of 2 pi over 3. We'll deal with all those in a sec. On the bottom, I have a cosine of 2 pi over 3 times a negative sine of pi over 3 plus a cosine of pi over 3 times a negative 2 sine of 2 pi over 3. And again, this is one of those places where it comes in handy to know the unit circle. So 2 pi over 3 is right here. At the point negative 1/2 comma root 3 over 2, and pi over 3 is right here at the point regular 1/2 comma root 3 over 2. So I'm just going to plug in a bunch of values. So I get negative 1/2 times a regular 1/2 plus a root 3 over 2 times a negative 2 times a root 3 over 2, all over, this is a negative 1/2 times a negative root 3 over 2, plus this is a regular half times a negative 2 root 3 over 2. Cool, so let's clean up this ugly mess. I seem to get a negative 1/4. This would be a 3, right? So this is a 3 times the negative 2. So I end up getting a negative 6/4. And I'm going to leave it as 6/4 because I already have a 1/4, and it's easier if I can leave them together. On the bottom, I seem to get a positive root 3 over 4. And then this would be minus a 2 root 3 over 4. Again, I'm going to leave everybody over 4 because it just makes my life easier. So this is a negative 7 over 4 and a negative root 3 over 4, negative 7 over 4 times 4 over negative root 3. I get that my answer is 7 over root 3, which is totally fine. If you want to rationalize, you could make it a 7 root 3 over 3. That's also okay. All right. Let's try another one. So same idea, this time your r is cosine theta. So your x of t, or sorry, your x of theta is going to be r cosine theta, right? So you can either do that as a product rule or you could treat that as a chain because this is cosine of theta quantity squared. Either of those are fine. My y of theta is going to be r sine theta, which is definitely still a product rule. So you could either do, like I said, x you could either do as a product rule or you could do it as a chain. So dy dx is dy d theta on top of dx d theta, right? So my dy d theta is going to be u dv plus v du. And on the bottom, dx d theta is going to be a 2 cosine theta to the first times the derivative of cosine, which is negative sine, right? So my dy dx evaluated when theta is a pi over 4 is, and it's helpful to know what values are at pi over 4, but at pi over 4, so just a reminder, at pi over 4, everybody's a root 2 over 2. So I get that this is a root 2 over 2 times another root 2 over 2 plus a root 2 over 2 times a negative root 2 over 2 all over a 2 times a root 2 over 2 times a negative root 2 over 2. Well, the numerator ends up being a 0 because this number and this number are the same. So I end up getting a 0 on top of what seems to be a negative 1. Yeah. So, and so I just get 0, and that's it. All right. So we're going to give the equation, given the equation, rather find the instantaneous rate of change of r with respect to theta. So instantaneous rate of change of r with respect to theta. This is asking you for dr d theta. That's it. You're just differentiating with respect to theta. So, so dr d theta or r prime of theta, if you prefer, is just old school differentiation. This is a quotient, so I'm going to need a quotient rule, right? So I'm going to have low d high minus high d low. Draw the line, square the low. And then I'm going to plug in a value. So I want dr d theta evaluated when theta is 3, or you could just say r prime of 3. That would be fine. And so that's going to be a 9 plus 1 times a 5 minus a 5 times a 3 times a 2 times a 3, all over a 9 plus 1 quantity squared. So I get 50 minus 90 all over a 10 squared. I think I get negative 40 over 100 or negative 0.4. All right, that's it. So given the equation, same idea, we're going to find the instantaneous rate of change of r with respect to theta. So that just means find r prime of theta or dr d theta. So dr d theta or r prime of theta, whichever way you want to write it. This is going to be a product, right? So u dv is going to be the derivative of cosine, which is negative sine of the stuff times the derivative of the stuff, right? So this is u, this whole thing was my dv, plus v, which is cosine of pi theta, du, which is a 2 theta. Right? So this was v, and this was du. All right, so I want r prime of 5, right? So that's going to be a 25 minus, this is going to be a 0 because negative sine of 5 pi, anytime you're at a whole numbered pi, the sign is 0 times pi, so that's a 0, plus this is going to be the cosine of 5 pi times a 10. So I get 0 plus a negative 1 times a 10, right? Because odd numbered pi's live over here, right? That's where 5 pi would be. It's also where 1 pi and 3 pi and 7 pi and 209 pi would be. So I get a negative 10. All right, So we talked a little bit about this in the last video. So if you're asked to describe the motion relative to some fixed location, like the pole or the origin or the x-axis or the y-axis, you always need two pieces of info. And I did talk about this in another video just without the visual because I'd already prepped it for this slide, and here we are. So you need to know where the particle is at a given time, right? The position. So is it above the y-axis, below the y-axis, above the x-axis, or left of the, above the x-axis, below the x-axis, left of the y-axis, right of the y-axis? Is it, where is it relative to the pole, right? And then you need to know the sign of the velocity at the given time, right? Is the particle, what direction is the particle moving? So here's the example I used, and it's almost verbatim the example that I used without the diagram the other day. So if you're standing at 16th and Norris and you're walking east, then I know that you're walking towards Broad Street because I know where you are and I know which way you're walking. So I can decide if you're walking towards or away from a fixed location, in this case, Broad Street. If you're standing at 12th and Norris and walking east, I can say that you're walking away from Broad Street because I know your physical location and I know which way you're walking. Together, those pieces of information are enough to tell me which way you're walking, to describe your motion relative to that fixed location, which is Broad Street. So we're going to go ahead and try one of those in a sec. So you'll likely see one of these three questions at some point on your AP exam. At the given time, is the particle moving towards or away from the x-axis? At the given time, is the particle moving towards or away from the y-axis? Or at the given time, is the particle moving toward or away from the origin/pole? In all three cases, you need the position relative to that fixed location, the velocity relative to that location, and then essentially the sign of those quantities being opposite means the particle is moving towards whatever the location is, right? So you're to the west but moving east. If the signs are the same, then you are moving farther from the fixed location because you are already east and you are moving more east, etc. So that's kind of the idea. So let's go ahead and walk through two examples of that in polar, like an example and a practice problem, and that'll be it for our video. So this is a calculator problem. A particle travels in the xy plane along the curve given below. Given the information about the curve, at the moment when t is 4, is the particle moving towards the origin? Justify your answer. So what I'm going to need to know is I'm going to need to know what the radius is at 4, and I'm going to need to know, so the two things I need, right? I need to know, 1, what is r of 4, because we were told that t is the same as theta, right? And 2, what is r prime of 4? And that's going to be enough for me to answer, like dr dt or r prime of 4. So I can go ahead and start by finding r of 4 because, again, I was given that t and theta are the same. So the time and the angle are the same, right? So that's going to be a 1. Oh, sorry, it's a calculator section, my bad. So we do have a parametric mode, and we have a polar mode. Similar to parametric, you will find that sometimes polar mode is not as useful as function mode. So I can put this in, so theta to the third minus 2.8. I can definitely use polar mode, but just to be clear, it's not always as useful. So if I go to second calc, I still have value as an option. So I'm going to go ahead and do second calc and pick value. And I want when theta is 4, right? So I'm going to hit 4, enter, okay, and I'm going to get a value. So the problem is, right, that when I find the value, they give me the value in terms of x and y, right? So you can, oh, my bad, that's not the pen. So you can put this in as r1 of theta in polar mode. And you can do second calc value, right? So you can do second calc value. The problem is if you do second calc value, it's not going to give you the radius. It gives the x comma y. Now, that's okay. I'm going to jump back up for a sec. All the way up here. You do have a formula that allows you, which is Pythagorean theorem, to find r if you know x and y. I'm going to argue that even though you can use polar mode, right, so you could use r squared equals x squared plus y squared, but that's a lot of work, right? The other option, right, and I am showing you both of these options, the other option is to stay in function mode. Right? The other option is to stay in function mode and essentially treat this as y of x equals 1.5x times x cubed minus 2.8 in my calculator, right? I know that it's actually these variables. So I don't write this on the AP, right? I don't write this on my AP. I don't write this for anybody else. I know that the variables represent this. So I want to show you why that's advantageous. So let's quit out of here. Let's go to mode and let's go to function. This gives me an easier opportunity to find what R is. So if I put this in, again, there are different values to each of the different modes. I just don't want you to get locked into your head that because a question is polar, you have to be in polar mode, because the polar mode in your calculator does not have the same functionality as what you're used to seeing. So now, if instead I go to second calc and I pick value, now when I put in my x is 4, because x was my theta, there's my R value right out. It spits the R value out for me. So if I do it this way, when I do second calc value, right, if I do second calc value, it just gives me an x, which remember is actually my theta, so x is 4, right? And it gives me a y, which I have standing in for my R, that is a 367.2, right? So that gives me that value, and I don't have to do this to find R. So I'm going to argue that that's the better plan. So I know you can be in polar mode, but I'm going to argue you don't have to be, and it's actually not as useful. By the same token, in either mode, I can do second calc, and I can pick dy dx, right? So if I do second calc and I pick dy dx, which is an option in both modes, I want dy dx when x is 4, and it'll find it for me. So I do second calc dy dx, right? I get dy dx. Oh, let me actually clarify. So I do second calc dy dx if I'm in function, because remember my x and y, but if I were in polar, right, if I had picked the polar mode, I would have had to do second calc dr d theta, right, because that's what we wanted. And I'd get the same value, right? I'm going to get the same value, and I'll show you. I'll switch back to polar in a second, show you that I get the same value. So I get this, right? So what matters here is that R is greater than 0, right? Oh, let me actually be specific. R is not always greater than 0, right? R of 4 is greater than 0. So for my answer, and I'll go back to polar mode in a sec. For my answer, R of 4 is greater than 0, right? It's positive. And R prime of 4 is also greater than 0. So it's moving away from the pole, right? Because if it's already positive and then it's getting more positive, then R is getting bigger, right? If I go back to mode for a sec and go back to polar, I do want to show you that, so if I did second calc, I would pick dr d theta, because remember, the reason I picked dy dx is because my y was actually my R and my x was my theta, right, in my notation. But I'd pick dr d theta, I'd pick it when theta is 4, and you'll see I get the same answer. So there are different ways to do this. Again, functionality-wise, no pun intended, I think function mode in your calculator is often more useful, but you have to do the variable switching. You need to say in your head, oh, hey, I'm using y and x, but I know that they stand for R and theta. All right, so let's go ahead and try this one, right? Same idea. Again, I don't care functionally what you do, right? You can either be in polar mode and do R1 equals 4.1 theta divided by, in parentheses, theta squared plus 5.2, right? Or you can be in function mode and know that you're using y1 and you're using x's, but they actually stand for, so this is in your brain. You don't write that you did this, but I'm writing it because otherwise how are you going to learn to do it, right? I think that this is the better option. I think you get a lot more functionality out of the regular function mode, but it is what it is. So the two things I need, right? I need to know what R of, they said moment in t is 2. I need to know what R of 2 is, and I need R prime of 2. And I can make my calculator find both of those things. So if you're in polar, it's fine. But again, you're going to have a hard time finding the value because you're not going to get R, right? So it's not wrong to do this. 2 plus 5.2, right? It's not wrong to do this. But if you graph this, if you do second calc and you pick value and try when theta is 2, see how you're not getting R. You're getting, so if you do it this way, you're getting x and y, and then you'd have to use x squared plus y squared equals r squared, and it gets a little bit more complicated. So I'm going to suggest that you go to function mode and instead type in your 4.1 x yeah, that one was multiplication, sorry, my bad, divided by X squared plus 5.2, right? And I graph it, right? And I'm going to go ahead and do, second trace, and I want value, and I want it when X is 2, because that would be my theta, right? And so I get that this is approximately a 0.891, which is greater than 0. That's really all I care about, right? And then I can do second calc. And again, here I want dy dx because I'm using, I know that I'm using my y and x to represent r and theta respectively. And I get 0.058, which is also greater than 0. So, so this thing is moving away from the pole, right? Because they have the same sign. And that's the gist of it, right? Let's just go back and check real quick. Yep, sorry, mode. I feel like I might have accidentally made this multiplication. Yep, I did, hang on. There you go. All right, so then if we graphed, you'd see it looks like this, and I could do trace and 2, sorry, but it wouldn't actually make my life any better, right? Because I'd still have to use Pythagorean theorem to find r, and it's a little bit tricky. The other reason it's tricky to use Pythagorean theorem to find r is technically your r could be a plus or minus, and since all you really care about here is the sign of r, not knowing if r is plus or minus is sort of problematic. So again, I'm going to suggest that you use function mode, because if you had done polar mode, you'd have to do r squared equals x squared plus y squared, but then when you square root, you don't know if you're taking a plus or minus version, because you can't know that easily, right? And the whole point of this question is that you need to know if r is positive or negative at that point. So that's it for this video.